All right, so today we're going to talk about 10.2 and 10.3. 10.2 is, we're going to be talking about hyperbolas. And so if you remember last week on Wednesday, we talked about conic sections, the different slices of those cones that we have. And we talked about how we could kind of know from the equation what shape we were going to be getting. I thought a lot of the answers on the discussion were really spot on about what we're looking for in terms of clues. And so just as a very quick reminder, let's talk about the ellipse and the circle. And if we think about how they are similar or how they are different in both cases, we can take a cone and take a slice of this said cone. And depending on how we cut it, we'll get one of the conic sections. And so I think in particular, if we took a slice that was sort of like this, it went through the cone, but just one of them, and kind of on a diagonal, we ended up with an ellipse. And we also realized that from the equation, we could have something like x minus h squared over a squared plus y minus k squared over b squared equals 1. And one of the things that I asked you to sort of make note of on Wednesday was that this in between here was actually a plus sign. And so if we thought about how to modify this equation for the circle, what would folks suggest that I change about both the diagram and the equation?
For the equation, you would change a squared and b squared to r squared because they'll have the same radius.
Right. So we could have an r squared down here, exactly. So whatever that number is on the denominator, if it is the same, we know we have a circle. And how might we change the diagram?
You'd make a slice that's parallel with the base.
Draw something like that. It is parallel to the base, indeed. And one last thing to think about here, this equation of the circle might also look like x minus h squared plus y minus k squared equals r squared, right? If we multiply the entire equation by the denominator on that left-hand side, we'll end up with an equation with no fractions, but on that right-hand side, we'll be able to see that we have that radius squared. Okay. And so that's what we talked about last time. But if we were to go ahead and take that cone that we have, and this time draw a slice, maybe something like this, where we cut through the top and the bottom cone. Then the name that we gave this was the hyperbola. And the equation, it turns out that it is really similar to the ellipse equation. So let's go ahead and grab this equation, bring that over here. We're going to modify one thing for this equation. Okay. And turns out that one thing is instead of a plus sign in between them, we actually have a minus sign. And it's such a small change, but it means that instead of getting an oval kind of shape like we did here for the ellipse, we end up with sort of two parabola situations, all right, that are facing outwards. And that's what that minus sign does. Now, I do want to also make note that it could also be y minus k squared on the top of the first fraction and x minus h squared on the top of the second fraction. Okay, so if we are looking at subtraction, then we actually do need to think about whether the order matters or not. And what I mean by that is, we can do this with a simple example here. What's 1 minus 2? Yeah, 1 minus 2 gives me -1. What's 2 minus 1? Yeah, we get +1, right? And so we don't get the same number. 1 minus 2 is going to give us something different than 2 minus 1. And so that's why we're going to need to be super careful when we have the subtraction here in asking ourselves, does the x come first or does the y come first? Okay. All right, so before we hop into a list of all things equations, let's go ahead and re-warm up our brains with this idea of completing the square. All right, and we're gonna do something very similar to what we did on Wednesday of last week, where we're gonna start by grouping the terms in their like terms. And so we might have our x's, we have a 9x squared and a 36x. We'll write those together. And then we have a -4y squared and a -40y. And then we have this -388 that we're gonna say, hey, go sit on the other side while we take care of this completing the square. Okay. All right, so let's clump our like term. We get 9x squared minus 36x minus 4y squared minus 40y equals 388. All right, so all we've done is sort of rewrite our terms so that the ones that share the same variable are next to each other. And now we're going to do the same thing we did last time, where we factored out a common factor, not the greatest common factor, but a common factor. And in particular, in the 9x squared minus 36x, we would factor out a 9. So we're left with 9x squared minus 4x. And that would be equivalent to my 9x squared minus 36x. What number should I factor out of the y terms, the blue ones?
Just a 4.
Ah. Let's be a little bit more specific. We do have a 4.
A -4?
Yeah, we're actually going to be factoring out a -4. Okay. Now I'm going to put a big red star by this, a few of them, because that minus sign is probably the easiest place to make a mistake, right? And I point that out to say, if you make that mistake, you are not the only one. And I would like us to just be super, super aware of this very common mistake, right? So we factor out the 4. What are we left with inside our parentheses?
Y squared plus 10y.
Yes, y squared plus 10y. And as I'm finishing doing the color coding, take a moment and just make sure that you feel good about why that second sign all of a sudden became a plus. Okay. So this part, just like we did on Wednesday, but all of a sudden now we're factoring out a -4 of the second group of terms. And so if we think about, if I distribute it back, I should get to where I started. A -4 times y squared gives me -4y squared. But in order to get a minus sign up here, I need a negative times a positive to give me that -40y. Okay. All right. Once you've done that part, the rest of it is just like we did on Wednesday of last week, okay? And so we take our x's, we have 9, whoops, we have 9x squared minus 4x, and half of 4 is 2, and 2 squared is 4. So I'm going to write a 4 here. Minus 4y squared plus 10y plus, what number am I adding inside the parentheses there?
$25.
Yeah, because we're going to do 10. Half of 10 is 5, and 5 squared is 25. Okay. All right, let's go ahead and balance out our equation though. On the right-hand side, I'm not going to just add 4, but I'm going to add 36. So 9 times 4. And on the, to compensate for this 25, I'm actually going to be subtracting 4 times 25. So here again is another moment where making sure you have the correct sign in the front is going to be really helpful. Okay. We rewrite this as a perfect square. We get 9x minus 2 squared minus 4y plus 5 squared equals, we do a little arithmetic on the right-hand side and we get 324. Let's go ahead and divide. We're going to divide by 324. It's okay that it's a really large number, but we'll divide away that so that we get on the right-hand side a 1. And does anyone have a simplification for either the first fraction or the second fraction? Go ahead and throw that in the chat. Let's see what we get. I agree. I think there's a 36 in the first denominator, which I'm going to preemptively write as 6 squared. And then the second one should give you a denominator of 81, which we can write as 9 squared. And so this, completing the square, is going to be what we are looking at to do with the hyperbolas, just like we did with the ellipses. The only difference is there's a couple spots where we have that negative sign. We just need to be super careful about that sign. Other than that, the numbers here tell us a lot of the same information that we had for ellipses, okay? It's just that our resulting shape will be a little bit different. And so what I actually want to do is go ahead and take a look at sort of a general look of what these hyperbolas look like, okay? So on this next page, we'll see that a classic hyperbola has those 2 branches, right? One from one of the cones, one from the other cone. And some of the words here that we have here are, should be familiar to us. We've still got a center. We've still got vertices. And we still have foci. But a note I want us to make for ourselves is that foci are in the same direction as the vertices. Okay, just like an ellipse. All right. However, the foci in a hyperbola are farther away from the center than the vertices are. Okay. Let me sort of zoom back in for a moment. We look at this diagram, we've got our foci or our vertices right here, but you'll notice that our foci have a greater distance from the center. Okay, before in the ellipse, they were sort of in the inside of the ellipse, but now since those curves are facing outwards for the hyperbola, our foci are still sort of inside that curvy part, okay? A couple other important things to note. Just like we had two sort of orientations of the ellipse, right? We had one that was like an Ernie with like the wider than it was tall. And then we had the Bert where it was like taller than it was wide. Similarly, we have situations where we either have our hyperbolas open up sideways like this, or we have them opening up and down like this. And so one thing I'd like us to write down here is for the ones that face sideways, we have x minus h squared over a squared minus y minus k squared over b squared equals 1. So anytime we see the x coming first, the branches open up sideways. But if we have the y first, y minus k squared over a squared minus x minus h squared over b squared equals 1, right? So if the y comes first, then we're going to end up with a hyperbola that opens up and down instead, okay? We're going to go through a few examples, really thinking about why we're making the decisions that we're making. However, for those of you who are really like having some equations to go back to, here's a little table with some equations, all right, that you can kind of plug in and compare and contrast to what the actual equation is that you have. And there are two things that I want us to note on this page. The first thing is this Pythagorean relation. C squared equals a squared plus b squared. Okay. This is different than the ellipse one. So when you're making your reference sheets for Wednesday, I would highly encourage you to make sure that you have these Pythagorean relations written down somewhere. And in particular, thinking about what is the Pythagorean relation for ellipses and what is the Pythagorean relation for hyperbolas, right? If you only write one down, you're missing one. You might not know which one, but you're missing one of them, okay? The second piece that I want us to notice is we have asymptotes in this hyperbola. And in fact, we have slant asymptotes in this hyperbola. And that's actually going to be part of how we draw our diagrams, is that we're going to draw a few points, a few important points, and then we're going to draw the asymptote. And then after that, we sort of sketch the hyperbola part in, okay? So let's jump into a few examples. Let's see what it looks like. So I think sometimes, you know, it's easier to figure out what questions you have once we're actually trying it out. Okay. So here we go. let's complete the missing equation or missing information, right? So we've got a grid here. I look at this equation and right away, I zoom in on the fact that we have a subtraction sign in between here. And so I know that I'm looking at a hyperbola. Now, in particular, is my hyperbola opening up sideways or is it opening up and down? And what tells you which way? Good. The fact that the X comes first means we have a shape that's going to end up looking something like this. Okay. Another thing that folks might do is write 9 as 3 squared and maybe write 16 as 4 squared. Okay. But I bet that you know where the center is. What would be the coordinate of our center? You see a 1, 2 there. Do we agree with that? What do other folks think? All right, I would agree. We are going to have a 1, 2. Then maybe a note we want to leave for ourselves is that we've got to switch those signs of what we have in the equation, right? X minus 1. If we solve for X, we get 1. Y minus 2. If we solve for Y, we get a positive 2. Okay. Now, if we were looking at an ellipse, would you think that the 3 or the 4 tells you about the vertices? Yeah, I think one of the points we talked about on Wednesday of last week was that the bigger number tells us about the vertices. One of the things that is really important to note in a hyperbola is the vertices actually depend on the first variable. Meaning it's the number in the denominator of the first variable that tells us where the vertices are. The co-vertices will be where the second variable goes. Okay, so in this case, the order matters in so many different ways. Okay, let's go ahead and plot these things first and then come back and fill in the equation for the vertices and the co-vertices. And the first thing I'm going to do is I'm going to plot the center. So I'm going to go to 1, 2, and I'm going to have my center point. Right. Now I'm going to do something that I did for ellipses, which is the number under X tells me how far I go outside to side. The number under Y tells me how far I go up and down, and I'm going to do the same thing. So from X, I'm going to go out 3, out 3. And from the center, I'm going to go up 4, 3, 4, and 1, 2, 3, 4. Okay. But I'm not going to draw an ellipse. Rather, the points that I've drawn, I'm going to connect as a box. All right, so I'll give you a moment to draw that box. The asymptotes go through the corners of the box, like the diagonals of the box. Meaning this is one asymptote. This one is another one. All right, we've got two asymptotes here. Those asymptotes help us draw the hyperbola. Right, the rest of this we sort of sketch, but these characteristics right here, all I need to do now, and I'll do this in the actual pen in a second, but I'm going to draw one branch kind of like this, and the other branch kind of like this. Okay, so you see how those yellow asymptotes are kind of like guiding lines for what we're doing. So let me zoom back in, and I'll end up with one hyperbola branch over here, and then another hyperbola branch over here. Okay. Now, these points right here, the ones that I actually have the hyperbola at, those are my vertices. And so if we think about how we got from the center point to those sideways points, we took our center point and all we did was add 3 to the x value and subtract 3 from the x value. And so we can think about our vertices as 1 plus or minus 3, comma 2. And the co-vertices then would be these points up here. And so that would be 1 and then 2 plus or minus 4. Okay. Let me pause here for a moment because some of this is very similar to the ellipses and yet it's also different, right? So let's take a moment, let's kind of pause, see where we're at, what kind of questions are coming up. If there's anything I can clarify for you right now.
So I had a question. What's the purpose, I guess, of the coverts other than just the box? Or
They help you figure out where your asymptotes are.
okay.
In particular, in this case, they tell you how steep or not steep your asymptote is.
Okay, thank you.
All right. We got 2 more things that we need to do here before we're done with this particular problem. Okay. One of those is we're going to identify where the foci are. And so we want to remember from the diagram that we just saw, the foci are going to be somewhere in here, like somewhere inside of the hyperbola. Okay. And so the Pythagorean relation we have for this is c squared equals a squared plus b squared. And so this c squared, that is going to be the longest distance because it's all the way out here. So the nice thing about this is we can say we have our a squared, which is 3 squared, plus b squared, which is 4 squared. And so we end up with c squared equals 25, or c equals plus or minus 5. All that tells us is from our center, we're not going to count out 3, but we're going to count out 5 units to get to the foci. So if I count out 5, I'll get 1, 2, 3, 4, 5. And if I count out 5 for the other way, I get 1, 2, 3, 4, 5. And so the way we would represent this is we would say 1 plus or minus 5, comma 2. All I'm doing is changing the x value of the center point, not the y value. All right, so as you're working through these problems, it's really helpful to be purposeful about what you are drawing. Like, are you drawing a hyperbola? Are you drawing an ellipse? And that's one of the reasons that I ask us to kind of identify that up front. Right? Sometimes when we get into the problem, all this arithmetic, we sort of get lost about what we're doing and what our end goal is. But when we bring it up and put it right at the top, like, this is what I want my end picture to look like, it makes it a little easier to think, oh, okay, I don't want to draw an oval. I want to draw something that's facing outwards, either to side or up and down. Okay.
I have a question.
For sure. What's up?
Why are the foci like on the shorter side, I would say?
Yeah, that's a great question. So the foci have to be sort of determined where the branches are. So if the branches are side to side, the foci are also side to side. But if I had branches up here, my foci would be up here. So it depends on which way your hyperbola opens. With the ellipse, we are looking at like the bigger number, but when we're looking at hyperbolas, it's more about like which direction does it open, okay? I know it's a little confusing. The rules are different, and that's why we really want to take the time to think about why. So questions like that are super great, okay? The last thing that we need to find is going to be an equation for these lines, okay? Now, one equation that I want us to remember is when we think about equations for lines, we often think y equals mx plus b, right? We use that, that's like our bread and butter when we're in high school. And it has its uses, but you need to know the slope and you need to know the y-intercept, okay? So it's not that y equals mx plus b is a bad equation, but there's an alternate form of this equation, right? And we call this alternate form point slope. This point slope form we are going to use now, and we will use a lot in Math 150 in the spring. Okay, so this new equation I'm about to write on the right-hand side, it is something that will 100% come back up again, and it's going to be really useful. If we learn this now and it's something we can hang on to in our brains until the spring, it'll be a little bit less work that we have to do there because we're actually going to be applying that. So this point slope form is as follows. Y minus y1 equals mx minus x1. Right. The only things that you need to write this equation, you need a point and you need the slope. And we're going to choose really wisely. And notice that both asymptotes go through the center point, right? Here's our center. One asymptote goes through that. The other asymptote goes through that. And so that point is what we're going to use as our x1 and y1. Right, so in addition to the colors, let's kind of write those down, that our x1, y1 are going to come from our center. And then the slope of these, once we have our diagram, we can count rise over run. All right. So let's plug in our y1. We're going to leave a space for the m and then x minus x1. So I've plugged in the x value of my center, the y value of my center. The only thing I need to put in here now is my slope. And the slope, I'm going to scroll back up and we're going to count the rise over run from our diagram. Okay. So let's zoom in a little bit here. Take a moment, count the slope for the one going this way. All right. And after you're done with that, go ahead and count the slope for the one going this way. When you think you have it, go ahead and type that in the chat for me. All right, let's kind of see what we have for our slope. Right, I see a 4/3 in Dallas. Is that for the first one or the second one? It's the first one, I would agree. That's a great question. Anyone feel like they can clarify that? How do we count that slope? What does that mean?
You basically start at the center point, go up in this situation to the covert. And so that's up 4. And then you go right until you get to the side of the box, which is the vertice in this situation, which is 3. And then for the -1, you just flip the bottom sign because you're going left.
Okay. So in other words, you were saying, here's one point, here's the other point, and then counting the rise over run to get there. Yeah. So Ellie, if we count that, we start here. We're going to go up 1, 2, 3, 4. And then how far do we go over to get to the corner of the box? We're going to go 1, 2, 3. So our slope is going to be, for this line, positive 4/3. Does that make sense?
Yeah, thank you.
Cool. All right. So take a moment then and do the same thing with the second asymptote, right? You can pick any points you want, but I think the center and maybe like this bottom corner could be a good one. And I think once we count that way, we'll end up with negative 4/3. All right, so we end up with the slope of this one being positive 4/3, but the slope of this one being negative 4/3. And since we're trying to find the equations of both of them, we can say plus or minus 4/3. And that is what we have down here. All right, so we'll have plus minus 4/3. So when we say count the rise over run, what we mean is go up to our diagram, find that yellow line, pick any 2 points on there and count our rise over our run. Okay. All right. So let's get this all on one page here for a moment and see what kind of questions we might have before we move on. I think we'll do one more example before we move on to our break.
I had a question. So the only way to really find out if it's vertical or horizontal is based off of the X and Y. And then with that, I don't know if we went over it, but the A and B position, it doesn't change. Like if Y goes to the front, it doesn't make B squared at the front, right? Or it doesn't really necessarily matter.
So if the X is in the front, you're right that tells us it opens sideways. But the number under the X will still tell us how far we go out side to side. And the number under Y will still tell us how far to go up and down.
Okay, regardless if Y is in the front or X.
Right. Yeah.
Okay.
Yeah.
Thank you.
You're welcome. All right. So let's go ahead and skip down to example number 5. Okay, let's take a look at example number 5. All right. And so I wanted to skip to example number 5 because this is one where we'll be able to practice that idea of completing the square. Okay. And in order to do that, it would probably be really useful for us to clump our like terms, just like we did in that completing the square example from earlier. Okay. Now, if I start to rewrite this, I'm going to get 9y squared minus 36y minus x squared plus 12x equals 36. Right, so I've moved the 36 to one side. I said, let me just put all my x's together over here, and let me put all my y's together over here. And we're thinking, let's go ahead and find that common factor, not necessarily the greatest common factor, but a common factor. All right. And so when we pull out the common factor in the y terms, we'll get 9y parentheses y squared minus 4, 4y. What is this blue part going to look like if we take out a common factor?
-1.
Yeah, I'm going to have a -1. And what goes on the inside here?
X squared plus 12 or minus 12x.
Yeah, there we go. Right, so this minus sign, we got to be careful about all our signs all the way through. Okay. All right, from here we complete the square. We've got 9y squared minus 4y plus 4 minus 1, y squared minus 12y plus 36 equals, now I got to balance everything. So I've got the original 36 here. I'm going to add 9 times 4, and I'm going to subtract 1 times 36. And so we end up with 9y minus 2 squared minus x minus 6 squared equals 36. We've got one more step. We're going to divide both sides by 36. And so once we do that, we'll get y minus 2 squared over 6 squared minus, whoops, 2 squared minus x minus 6 squared over 6 squared equals 1. So a couple skipped steps here. Take a moment, make sure you know where all these numbers come from or where they went.
I had a question.
For sure.
Just to clarify, so the reason why we're changing the sign from addition, even though we're adding into like the x squared minus 12x plus 36, even though we're adding the 36 to do the completing the squares, it's basically like subtracting that, and that's why we're subtracting it on the other side of the equal sign. Because that negative sign is out there.
Yes.
Okay.
Yeah. So all those come from the blue term, whereas this 9 is positive and so is this 4. That's why this is a plus.
I have a question about this. So why didn't we put the x values first?
We could, but it has the negative sign.
Does the negative just indicate that it goes after then?
What if both y and x are negative?
Then I bet we'll be able to factor out a -1, and that might give us a different shape. But for our cases, we're really looking at either they're both positive, like the first one is positive and so is the second one, or if that other one is negative. But if you're curious, I would encourage you to kind of play around on Desmos and see what shape you would get if you graph that. It may or may not come out to a shape. I think that would be an interesting exercise to try. Cool. All right, so we've got this minus sign. And by convention, and sort of as Ellie pointed out, we keep the positive one first, and then we have the negative one second. And so this means that we're going to have a hyperbola. But in particular, this one, because the y term comes first, is going to look like this. So we're going to have it facing up and down. Right? And the reason we know it's up and down is because the y comes first. Right? All right, let's find that center point. What do we have, and listen to this question carefully, what do we have as the x coordinate of the center? Yes, very nice job. I would agree 100% with Ian that 6 is the x coordinate of the center? What's the y coordinate of the center? 2. Very nice, very nice. 6, 2 is our center, not 2, 6. Where would someone who got 2, 6 have gotten the center from? What mistake did they make?
They considered x was first.
Exactly, right? They were like, well, I don't know. We just always start with this one and then this one, right? But we have to be really careful about what we're looking at and notice we want our x coordinate to come first and then we want our y, okay? So really nice job there. All right, well, let's go ahead and draw this center. All right, I think I use this sort of seafoam green here. Our center is going to be at 6, 2. So 6, 2 is our center. Now, I might not know a lot else, but I know that from my center, I'm going to go plus and minus 2 in which direction? Is it going to be plus or minus 2 in the x direction or in the y direction?
The x direction, or no, y direction.
How do you know that?
Because the y is front in the front, and so we're trying to write the vertices right now.
Yeah, so the y, it has the 2 squared underneath. So from my center, I'm going to go up and down 2. So if I go up and down 2, I get to here and here. And I can write that as 6, 2 plus or minus 2. The co-vertices, it's like, how far do I go side to side from my x center? I'm going to go 6 in either direction. If I go 6 in this direction, I'll end up over here. If I go 6 in this direction, I'll be like just off the grid right over there. So if I think about how to write this, I would say 6 plus or minus 6, 2. Now, drawing these 4 points does not mean I'm going to connect them with an oval, right? I don't want to do this. And the reason I don't want to do this is because I saw a minus sign in between my x and my y fractions. And so instead, I'm going to connect them with that rectangle. And then I'm going to draw in my asymptotes. Whoop. That's terrible. Let's try that again. All right, so these equations, let's actually write those equations right now. Okay. So I know I want to use this point slope form. And in particular, I want to use my center as the x1, y1. The slope, I will just count from my picture, okay? So I'm going to go ahead and write in my y coordinate is 2, my x coordinate is 6. So I've got my x1 and y1. And let me zoom in on this picture and let me have you count the slope for the asymptotes. All right, let's make sure that's a skill that we feel comfortable doing. right, looks like we've got a 2/6 or a 1/3. Anyone else confirm that? Is that what we're getting when we count? No confirmations?
Just to clarify, so counting the Reisman run, we count to one vertice and then to the corner.
You can pick any 2 points on that line. So if you want to count from this corner to this whole corner, that's totally fine. But you could also count from the center to the corner. Right, so any 2 points on that yellow line, if you count between them, that'll tell you the rise and the run. We should get plus or minus 2/6, which we can write as that 1/3. And this one equation will give us the equations for both of these yellow lines, because this one will have a slope of positive 1/3, but then the other diagonal will have a slope of negative 1/3. Okay. Now, my recommendation would be to sketch in your shape before you find your foci. Okay, sketch in your shape before you find those foci. In particular, I want my hyperbolas to be facing up and down. Matt, that's a great question. I think that one habit I would like us to get into is that if it's easily simplifiable, like 2/6 to 1/3, I would like us to do that. Okay. If it's like a weirder fraction that's a little bit harder to simplify, I think that's less important. But I think something like 2/6 would be good to sort of practice that mental math piece. Okay. All right, so let's sketch that hyperbola in. We've got a branch this way. We've got a branch this way. And my foci, are they going to be over here? Like sort of side to side? Or are they going to be up and down?
Up and down, like where the branches are open.
Exactly, exactly. They're going to be up and down. Okay. So let's make a note for ourselves, up and down. And let's go ahead and find out exactly how far they are up and down. So c squared equals a squared plus b squared, because it's a hyperbola. C squared equals 4 plus 36, because those are the numbers we had. That means c squared equals 40, and c equals plus or minus square root of 40. And if we think about our equations, we want to keep the same x value, but we're going to add and subtract that value to the y value. So we'll get 6, comma 2 plus or minus root 40. And so that should give us something that is about 6 units away. So 1, 2, 3, 4, 5, 6.3, I think is about there. And then 1, 2, 3, 4, 5, 6.3 is about there. So these foci are exactly like Ellie said, they are inside of where those branches go, right in there. All right, so folks, I think that is a good place to stop and take a break. All right, so it is 10:40 right now. Let's be back at 10:55. Just type that in here. Let's be back at 10:55. We'll come back, we'll do a couple more examples with the hyperbola before we go ahead and finish up with the parabola, okay? So I'll see everyone back here in about 15 minutes. All right, so before the break, we took a look at a question where we needed to graph a parabola, identify all these different features about it, and really work on that decision-making process. And I think there's so much power in identifying what it's going to be first, maybe just taking each one of these sort of step by step and thinking about, okay, well, if we know that these things have to go in this direction, where do I add this number? Do I add it to the X or do I add it to the Y? All right. And so what I'd like to do here is go ahead and take a look at a couple examples where we're given some information, we're actually trying to write the equation for it, all right? And in particular, I think these are going to really key in on that idea of the focus or the foci and how those relate to the Pythagorean relation and how we can create an equation from that, okay? So let's go ahead. Take a look at example number 7 and 8. Okay. So example 7 says, find an equation for the hyperbola that has its center at the origin and satisfies the given conditions. And so when we're looking for a hyperbola, we really want to note that we're thinking that we have a minus in between the two fractions, right? So we have a fraction minus a fraction equals 1. And then we are actually told that the center's at the origin, and that means that h comma k is actually equal to 0 comma 0. All right, so what that means is we're either going to be using an equation where we have like a y squared over a squared minus x squared over b squared equals 1, or x squared over a squared minus y squared over b squared equals 1. So either our x is going to come first or our y is going to come first. And I argue that if we draw a picture, like a quick sketch here, it should tell us which one of these letters comes first, either the x or the y. All right. So let's start with a diagram here. So we've got an x-axis, we've got a y-axis. If I'm going to draw my vertices, I'm going to go 0 and then +1 and -1. All right. And so what that means is that my hyperbola sort of go this way and this way. Okay. Now, even without drawing the foci, can you folks tell me, should we be using the first equation or the second equation?
First.
Yeah, we're going to be using that first equation. Okay. And so if we take that first equation, we can start to fill in some numbers. Y squared over something minus x squared over something else is going to equal 1. And so what are your thoughts? What number should go underneath that y squared? Yeah, we're gonna go ahead and put a 1 there because from our center, we're going up 1 to get to a vertex. So really we're thinking 1 squared, but 1 squared is 1. So we could just write 1. That would be fine. All right, now let's go ahead and plot the foci. So the foci are this 0 plus or minus 4. And so I could put that here and here. But that number is not the number that goes underneath x, right? And so to find this number, to find b, we're going to use c squared equals a squared plus b squared. We're going to use that Pythagorean relation, right? And so in this case, we have c equals, what does c equal in this case?
2.
How do we get 2?
Oh wait, no. 4
How do we get 4?
from the foci.
Yeah, exactly. This distance, 4 units from the center to one of the focus points, means that c equals 4. Right? And a equals 1. So we can plug those in to find b. All right. So 4 squared equals 1 squared plus b squared. I believe we get 16 equals 1 plus b squared. So b squared equals 15, or b equals plus or minus square root of 15. That means that underneath the x squared, I can put square root of 15 squared. Or if I wanted to simplify it all, I could say y squared minus x squared over 15 equals 1. Either one of those options would be fine. All right, well, let's try the second one right here. All right, I'm going to set up an XY grid just so we can sketch our diagram and use that to help us choose, should we do y squared minus x squared or x squared minus y squared? All right. So I'm going to go ahead and draw those vertices in. We got a 3, 0, a negative 3, 0. So from even just these 2 points, should I use y squared minus or x squared minus?
X squared minus.
Yeah, nice job, because these vertices mean my hyperbola branches open this way, right? And if they open this way, that means that we want to use this x squared one first. So x squared over something minus y squared over something else equals 1. All right, what number can I put underneath the x squared?
3 squared.
Yeah, we can put that 3 squared, right? This plus or minus 3, this distance right here, that distance squared goes underneath 3 squared. What number should I not put here?
5.
5.
Yeah, we should not put a 5 there, but we can use the 5 to find the other value, right? We can say 5 squared equals 3 squared plus b squared. And so we'll get 25 equals 9 plus b squared, or b equals, let's see, 25 minus 9 is 16. So we get a plus or minus 4. So underneath the y squared, I could write 4 squared. right? And this would be an absolutely fine answer. You could change the 3 squared to a 9 or the 4 squared to a 16. That would also be fine. Right. So let me pause here for a moment. See if there are any questions coming up about example 7 and 8 here. All right. I will say that numbers 9 through 11, let's go ahead and write this here. Numbers 9 through 11 are definitely more of a challenge level, okay? And I would say that they're not necessarily super challenging, but they're a little bit different than example 7 and 8. So if you feel like you've got a pretty good grasp on this, then I think 9 through 11 would be a great place for you to work. But if you're feeling like, oh, 7 and 8 were enough for me to focus on, then that's also fair, okay? Now, there are a bunch of other practice problems in here. The nice thing about having the equation means that you can throw this graph on Desmos and you can use that to check your answer. Because as you're working through completing the square, that should give you things like the center, the vertices, the co-vertices, and you can see those as you check on Desmos. All right. So if you are like, I would like to do some more practice problems, then these would be great ones to try, along with those other ones from the quiz you turned in on Friday that were about the hyperbola. Okay, and those ones from the quiz do have the answers. But if you also want to come in early on Wednesday for the office hours and work through some of these questions, that would be absolutely fine as well. Okay. So with that, we are going to stop our video here for 10.2.